So last time we saw how SysTick works, but can you give me some like real code that uses SysTick to create a periodic interrupt?
Okay, let's take an example. Here's
Yeah.
an example use case, if you will, of SysTick in its interrupt mode, SysTick interrupts. So the problem we're going to solve is we have a background thread, right? A background thread. And this is our task. We call it a thread or a background task, if you will. And this task's job is to take a global variable. We're going to have a global variable called count. And this count will just be incremented here. It'll just do a count plus plus, but it'll do it periodically, which means that this background task is going to run we'll set this period, it'll run periodically. And every time it runs, it's going to increment this count by 1.
Okay, so count is actually a time then.
Count
All
is
right, I get it.
a time.
All right, make it happen, Ramesh.
And the foreground thread is just gonna do some work. We won't worry about what it does. It does some useful work, and the
But
foreground.
it's something else.
Something else. That's the whole point. Foreground does some busy work, right? Whatever the busy work is. But we want to periodically go and increment that. Let's write the code for this. I'm just going to write it in parts. First, we will look at this variable count. So we're going to make this a global variable.
I got it.
And we're going to do our initialization. And this initialization routine is going to follow our simple idea. First, anytime we're doing any initialization, we like to first turn it off. So this is my control register is saying the start stop bit, which is basically my bit 0. I'm just going to write a 0 to it, which is going to make it stop. Okay. So we're not doing anything with it. Now that we did that, we're going to set our load register. We know that if I set the load register to some n value, then it's going to tick for n plus 1 number of ticks. So if I want to tick exactly for n, I'm going to make that n minus 1, okay, which is what we did here. So we set that. Now we're going to set our priority. Priority is part of this register, but the important point here is there are 2 bits here. And these 2 bits have to have a value of 1, 0. This is where the priority
to make priority 2.
Priority 2. So that's all we're doing here. So these are bits 31 and 30, and we're shifting it 30 times so that we can get it there and we can put it into that priority register. The next thing we're going to do is we're going to write the initial value to 0, and this will make sure that right off the bat from 0, when it starts loading, it'll load the value that is in my reload register, or which is my load register. And lastly, now that we've got everything going, we're going to start it. So we're going to take the start stop bit again, and we can now make the start bit be a 1. So we'll make the start bit be a 1, and we're going to enable our interrupts. The interrupt enable bit is going to be a 1, and our clock source is also 1. So that's our 1, 1, 1.
Got it.
Right. So we've initialized our SysTick, and what happens now? So we need some event to occur, right, John?
Yep. So when the value goes from 1 to 0, it should trigger an interrupt.
Yes. So when the value goes from val goes from 1 to transition to 0, we said that this will cause an interrupt. So this causing of an interrupt means that we need to write a handler for it. So we'll write a handler called the SysTick handler. And just to recall, all this really means is that somewhere in our interrupt vector table, there was an entry which corresponds to this interrupt, which happens to be interrupt number 15. And the entry there has been written to be SysTick handler, which means that's the routine that's going to run. So we as programmers are going to write this routine. So let's write this routine. So here is our routine. So all we're really doing is this count business, which we are incrementing the count by 1. That's all we're really doing. Now we're also doing some other.
But I have a question, Ramesh.
Yes.
Remember the count flag got set by hardware
Mm-hmm.
to cause this interrupt. How did the count flag, how did it get cleared?
So I don't know if it got clear. So let's clarify that. So we know that the control register has a bit, which is the flag bit. We said that this bit flag, which is 16, we said that the act of this interrupt, when this interrupt happened, we said this became a 1, right?
Yeah.
And actually, when this transition happened, it became a 1. One of the things that SysTick does is, as soon as this is done by hardware, as soon as the handler is called, and it's entered, when it enters here, it's going to clear this flag.
So
to a
it's
0.
automatically cleared.
Yes. And
Okay.
this act of acknowledging, this is what we call as acknowledging the interrupt. Now, in the case of SysTick, they're doing it implicitly for us. It's done implicitly for us. You will notice that for other interrupts, you have to, the software programmer has to do it explicitly.
Okay.
But here
So
we
it got cleared just by running the handler.
running the
Got
handler.
it. All right, Ramesh. I see you incremented count like you wanted to.
Yes.
But what about all those other things?
So all the other things we're doing is because we're gonna try and study this handler so that we want to see how much time. So we'll study some important characteristics of interrupts. One of the first things we're going to study is what is the context switch time. What do we mean by context switch? That is, some code was running. We had our main program running. We'll look at it in just a second. The main program was running and some line of code was running. This line of code got interrupted and the hardware did a bunch of steps. We already know this. It'll save context. It saves context. And it starts executing in our interrupt handler. It went off and started executing in our interrupt handler, which is my SysTick handler. It went off here. So the time that has elapsed between the time it finished this, time it got interrupted, to the time it enters is some amount of time. That is one of the key things we want to study. That's my context switch time. We may also want to study how much time a particular incrementing this takes.
Okay, so in other words, how long to run the task inside the handler?
Exactly.
Is
We want to profile.
Okay.
We want to profile the background thread.
All right.
Right,
So
a background task.
So the time between the second and third toggle would then measure how long the task took.
Yes, and
Okay.
this is our background task, and we want to know how long it took. So all these things we are doing are going to facilitate that measurement. Measuring these two. So let's take a look at our main program now. Here's our main program. We are going to call a few initializations, but first thing we're going to do when we work on any program that involves interrupt-based program is we will disable interrupts. We will start with disabling interrupts.
Why?
And so that we don't want an interrupt to occur while we are setting up things.
Okay.
Right? We'll disable. Right. And we know that there's a bit called the I bit, and the I bit is basically going to be set. The enable and disable will basically manipulate the I bit. So there is a instruction, we know what it is, but that instruction is going to manipulate the I bit and set it to be equal to a 1 to disable it. And eventually when we are ready to do it, we're going to enable it.
Got it.
So the enable is this guy is going to set it to a 1, this guy is going to make it a 0. So we are going to use some GPIO. Actually, we're going to use this both port A and port B. The port A is a toggle of the red LED, and this is, you could say that this is our foreground task. All it's doing is doing some busy work, right? This one line is our foreground task.
So we have two threads. this is the foreground thread, and
Thread.
the other one we saw was the background.
Background thread.
Got it.
And so we're going to do a few other initializations. There are some commented lines here, but let's focus on the main things. After we've initialized our launchpad, we're going to start our clock. And right now in this example, our clock is at 40 megahertz.
25 nanoseconds each, huh?
So it's going to be 25 nanoseconds per tick and not our 12.5 nanoseconds. Here's our count. We had already we declared it globally, and here we're initializing it to 0. This is the initialization of the count.
Why do we put 400,000 as our parameter into the enable, to the SysTick interrupt arm?
So you're talking about this value.
Yeah, why is
here.
that? Where'd that come from?
So let's look at the initialization. So we want our count to be incremented at every, it says 100 hertz. 100 hertz is 1/100th of a second. So that's 10 milliseconds. Every 10 milliseconds, I want to increment it. So it'll be 0 here, it'll become 1, it'll become 2, and every 10 milliseconds, it's going to change its value. And what does 10 milliseconds translate to on a machine that is clocking or ticking at 40 megahertz? So at 40 megahertz, 10 milliseconds is going to be 40. That's going to be.
Oh, I see.
And we know how to do this. If you're too worried about it, that's just 40 times 10 to the 6 times 10 times 10 to the power of minus 3, which is 10 milliseconds, which is what that gives you that. So now that we've established everything and we're ready to turn it on, we sit in a while loop and we start running. And we'll demo this code to show you exactly how it works when on an oscilloscope. One of the problems with trying to visualize what happens here is this 10 milliseconds where the interrupt is happening. In between these interrupts, the red LED is going to keep running. It's going to toggle a lot of times right there, because it's toggling practically every clock cycle, because this guy is going to run as fast as the machine runs. So we want to be able to visualize this. So we'll show you a demo of how this works on a real oscilloscope.